Disculpe. Muy bien, ¿usted? ¿Quién va a dar la presentación? Disculpe, director. ¿El invitado? Perfecto. Hi, this is the microphone.
Yeah.
Can you please put it in here?
Yeah.
Thank you so much.
Like this?
Yeah, can you speak a little bit?
Hello, hello. Can you hear me? Is it okay? Yeah.
Thank you.
Okay.
Thank you so much.
Yeah. Thank you. You're welcome. Still not. And I wonder whether.
We are going to try to connect the.
Yeah. Mm-hmm. Yeah, but it's a little small for the auditorium. But
Well, we cannot see, but we have a special point there. Exactly. Let me phone where is it?
maybe I need. It's on my screen. Just. Just if you just wait a second, then let me try to see whether I can. I never know how to, because it's now the point is on this screen.
You can use this pointer.
Yeah, that will work. Yeah, it's on this. It's somehow here, and I'm not sure how to. Yeah, I might be away, but yeah. Yeah. That should work. Yeah.
The next and previous.
Yeah. Okay. But I'm ready. Yeah. But
Hoy tenemos el salón de nuestra sesión del doctor Marco Sánchez, profesor de Gobierno para actividades Now we are going to switch the images to start with the
to be in Mexico and in Puebla in particular. So I will try to, I know that not all of you are familiar with what we do at the LHC, so I'll try to introduce the studies that we do with the Alice experiment. And I'll try to focus on the study of the quark-gluon plasma, and I'll explain what that means, or I'll try to explain. This is a picture of the Alice detector, and I'll come back to that as we go along. So to start, I wanted to explain briefly about particles and interactions. I hope you are familiar with this, but to set the stage, so you probably have seen the structure of the atom, and as you know, okay, so is this? The atom consists of electrons which circle the nucleus, and the electrons are negatively charged and the nucleus is positively charged. And electrons are fundamental particles. They cannot be split. But in the nucleus, you have protons and neutrons, and the protons and neutrons are not fundamental particles. They consist in their turn of quarks. And the quarks are bound by a different interaction than the electromagnetic interaction. The way we describe that in the standard model of particle physics is that the particles that participate mainly in the electromagnetic interaction are the electron and the muon and the tau meson, which are lepton, which are the heavier brothers and sisters of the electron, as well as the neutrinos. And the interaction is, in a quantum field theory, we say it's mediated by the exchange of photons. And some of you may have learned this in quantum mechanics. Now, then the interaction that we study is not the electromagnetic interaction, but the strong interaction. And the strong interaction is where the quarks participate. The up and the down quark are the quarks that are inside protons and neutrons, and then also there are heavier quarks, strange charm bottom and top. And the gluon is the interaction particle, is the particle that mediates the strong interaction. And in our experiment, we focus on the study of the strong interaction in bulk matter, so the solid state physics of the strong interaction. So another way to think about that is by thinking about energy scales and temperatures. Because as you know, temperature and energy are in an atom. That binding energy can be as low as 5 electron volt and as high as 100 kilo electron volt for very large nuclei. And if you want to ionize that in a thermal system, so to make an electromagnetic plasma, you're looking at temperatures of 10 to the 4, so 10,000 Kelvin up to 10 to the 9, so a billion Kelvin. And then the next step in binding energy that you can make is the atomic nucleus, where protons and neutrons are bound together in the nucleus, and the binding energies there are of the order of 1 to 10 mega electron volts, and the temperatures that are needed to ionize such a system are 10 to the 10 to 10 to the 11 Kelvin. Now, the system that we study mostly is the binding of quarks inside the hadron, and the binding energies there are larger than 100 mega electron volts, and that means that the temperatures that you need are 10 to the 12 Kelvin. Now, we normally quote the temperatures in energy because it is more convenient. So we say you need a temperature of about 150 MeV to break up the hadrons and to make a quark-gluon plasma roam freely in a large volume. conditions. You see it here, this is an aerial photograph of the area near Geneva. You see here the airport of Geneva. And the Large Hadron Collider has a length of 27 kilometers. It is drawn here in this picture, so in the landscape, in reality, you don't see it because it's all underground. But this is the size of the ring that we use to reach very high energies. The energies are started out at 7 TeV, and now we have 13.6 TeV, tera electron volt for PP collisions. And for lead-lead collisions, we normally quote the energy per nucleon-nucleon pair, and it is now 5.36 tera electron volt. But it's important to realize that a lead nucleus has 208 nucleons inside, 208 protons and neutrons. So the total energy is 208 times this number. So the total energy is much larger than the energy in proton-proton collisions. And the LHC can also collide particles. So we have had a run with xenon nuclei, and next year we will collide oxygen nuclei and protons with oxygen nuclei to kind of simulate cosmic ray events. Now here you see the Alice detector. This is the electromagnet that provides the magnetic field for the experiment. And then here you see when we installed the TPC and the other detectors around the transition radiation detector. And then finally here at the bottom, this is the detector close to the beam pipe. So here, this thing is the beam pipe. So the beams come from both sides, from this side and one from the other side, and the collisions take place here in the middle. And this detector is a large silicon pixel detector. It is like a big digital camera, which consists of 7 layers of detection layers, and has a total of 10 billion pixels. And the experiment was first thought of in 1993. That is when we wrote what you call the letter of intent, where we decided to start working towards building the experiments. I was not in the experiment at the time. And then the first detectors were installed before the LHC started running in the years 2006 to 2008. And we just have performed a major upgrade, which was installed until 2022. And we're now taking data with this upgraded detector. Now then a little bit more about the detector still. A schematic view of the detector. Some of you are very familiar with this, but I wanted to show it also to people who might not be familiar. So it consists of 2 parts. This part we call the central barrel, and this is the forward detector. In the forward detector, we detect mostly muons, which are like heavy electrons, identified by placing a big block or a big absorber in front of particles. So most particles are absorbed and only muons come through and are measured. This gray thing is an absorber, and there are 2 more, one more here, and this is to protect us from. And then here in the central barrel, several different detectors. In the middle, there's this inner tracking system that I just showed you in the photograph that is schematically here. Then there's a time projection chamber, which is a very large detector that also mostly detects the positions of the charged particles. So you use those to measure the curvature of the particles and the momentum. And then the detectors on the outside are different detector systems to identify particles, to measure the mass or the velocity of particles. And that way we can tell apart pions and kaons and protons, and also electrons and photons at mid rapidity. I won't go into detail at the end. I have a little bit more for our upgrades on the principles of how these detectors work, but I would like now to go towards the physics and to introduce that. I show you an event display. So this is a picture. Oh no, there's one more thing. Before I show you the picture of the event, one word about the collaboration. So ALICE is one of the 4 large experiments at the LHC, and we have about 1,000 physicist members and about 2,000 total members, including, for example, technicians and other people who work on the experiment. Participants from 40 different countries and 160 about member institutes. Here in Mexico, there's of course one of the 40 countries, and there are 5 institutes that participate in ALICE. And here you see a picture of we have regularly meetings, mostly at CERN, where we meet and discuss the physics program. Here's a picture from a meeting we had in March this year. And the total number of publications that the collaboration has produced is now 517. This is starting from 2010 until now. We do about 50 publications per year. So as you can imagine, this is a lot of work, and I cannot tell you everything we do, but I will try to focus on the quark-gluon plasma aspects of the work we do, and I will just show you a few highlights as we go along. So the quark-gluon plasma is produced in heavy ion collisions, and this is a picture of one collision made by our detector. So you recognize the structure that you saw before in a tracking system time projection chamber. Here's the muon arm, and every white line here is one charged particle that is detected by our detectors and then reconstructed using our reconstruction software, which does like a pattern recognition. And here on the outside, you see this is the transition radiation detector. There's a time of flight system for particle identification. And then there are calorimeters, which are represented by these bars. So now I will try to explain a few examples of what we can, by looking at particles that are produced, how we learn about the plasma. And the first thing that you may want to know is the temperature. Now, measuring the temperature is not as easy as it might seem. So I'll show you here the current results on our measurements of the temperature. If you want to measure the temperature of something that is very hot and that you cannot touch, you normally look at electromagnetic radiation, at the light that comes out of it, like you can do for the sun, for example. And so we do the same. Now the temperatures are higher, so also the energies of the photons are higher than those coming from the sun. And you see here on the left, you see the measured spectrum of direct photons, and you see this is as a function of transverse momentum, and the distribution is more or less exponential, which is what you would expect for a thermal distribution. And the temperature that we find is about 350 mega electron volts. So this is well in this 10 to the 12 Kelvin range that I mentioned before. One thing that is important to keep in mind here is that this temperature is a little bit blue shifted. The plasma expands, and the medium that emits the photons expands towards you, and the photons get a higher energy than they would have in the rest frame. Now, one way to get around this blue shift is to measure, instead of photons, to measure what we call dielectrons, so electron-positron pairs, which also come from photon-like emission, but now they're photons with a mass, virtual photons. And what you then measure is the mass distribution. And you see here the full mass distribution. What you also see nicely is that besides the thermal radiation, there are also electromagnetic radiation from the decays of hadrons, of other particles. And this is a very important background. And this peak here at low PT, a low mass, comes from pi zeros that decay into an E plus and E minus pair. And then here are the phi and the rho and the phi meson and the jet psi. But here in the middle, you can measure rather purely the thermal radiation, except that there's still a contribution of semi-leptonic decays of charm and beauty quarks. So at the moment, we have a precise measurement of the electromagnetic, the production of these pairs, but we still need to subtract the background to get to the temperature. So at the moment, we do not yet have the precision to measure the temperature with this technique. And I'll show you later how in the future we can do that with a better instrument. Now, another way to look for the temperature is to look at for things that melt in the plasma. And if I can change the slide. Yeah, so then you see here how that works. So there are certain bound states that are easy to measure and to recognize. In particular, the ones that have a charm and an anti-charm quark. These are the heavy quarks, and the mass is larger than the temperature, so they cannot be produced thermally by the plasma, but they are produced in hard scattering early on in the collision. And then the idea here is that if you have a bound state and you surround it with this quark-gluon plasma, there are so many charges around that the binding force is what you call screened, and the state effectively melts. So the charm and the anti-charm don't feel each other anymore, but they just feel all the charges of the other particles that are around. And the melting temperature then depends on the binding energy of this meson. And we can measure different mesons to get a sense of the temperature. And what we normally report is the nuclear modification factor is the ratio of particle production in lead-lead collisions to the particle production in PP collisions. And if this ratio is 1, then there's no melting, and if it's 0, then there's full melting. I'll show you the result. So this is the result for first for the beauty bound states, so the BB bar pairs, we call those epsilon mesons. And what you see here as a function of the centrality, so these are central collisions where the temperature is large and the quark-gluon plasma is large, and these are peripheral collisions where the temperature is lower and the system is smaller. And you see that in the small system, this REA, this modification factor, is about 1, so there's no melting. And then as you go more central to higher temperature, the mesons melt. And you see also that the epsilon 1s, which is more tightly bound, doesn't melt completely, while the epsilon 2s, which is a higher state that is loosely bound, melts more quickly. So you see that the yields, this suppression factor is much larger for the loosely bound state. So this is exactly in line with what you expect from melting in a hot plasma. Now, we also had measured this for the charm system. The meson is called the J-psi, contains a charm and an anti-charm. And there, let's first look at black points. This is from RIC, which is a lower energy collider. You see the same kind of behavior here, the clear melting as a function of what we call centrality, the size of the system. And at LHC, these are the red points, is what we measured. And you see that here there is a different behavior. First there is a melting, but then somehow it saturates and it stays constant. And this, we now understand, comes from a combination of melting and regeneration. And to appreciate that more, I will show you in the next slide the transverse momentum distribution of these particles. Here on the left, again, for this J-psi, the black points are, again, the results from these lower energies at RIC. And you see that they are always suppressed. And at LHC, we see the same suppression at very high PT, but at low PT, the suppression is much smaller. There's a kind of an enhancement, and that is this regeneration effect. And there's more regeneration at low PT where there are more charm quarks. So at the LHC, we produce many charm quarks in every collision, and charm and anti-charm quark can find each other and they can recreate a J-psi. And so you have two competing mechanisms, melting and regeneration. And the most recent result on this from Alice is shown on the right. So these were the first measurements that we did in this area. And now this is the precision that we have achieved with our current measurements. The blue points are the equivalent of these red points. And we have also now measured, this is measured at forward rapidity with this muon arm that I mentioned before. We have now also measured this at mid rapidity with a decay into electrons. And you see that at mid rapidity, this increase at low PT is even larger. And that is also consistent with this regeneration picture, because at mid rapidity, at small angles compared to the perpendicular direction, you have more charm quarks, and more charm quarks means more regeneration. So now this was to measure the temperature, and now I will go to measuring pressure and pressure gradients. And for that, I will show first a sketch again of the collision. So this is two nuclei, one coming towards us, one going away from us, and they collide. So this is a non-central collision where you have the interaction zone is not circular, but is rather an elliptic shape. And in fact, if you think of these nuclei, they consist of protons and neutrons. So the actual collision zone is not elliptic, but has an irregular shape. Yes, like this. So you see here the protons and neutrons. This is a simulation picture, a very simple simulation. But you see that if you generate one event, you can get very irregular shapes, and you can decompose this distribution into spherical harmonics, which are shown here. So this is the elliptic component, which is the dominant one. It is mostly an ellipse. But then there are third and fourth order components. So the third harmonic is the green and the fourth is the red. And now the nice thing is that So this is a spatial distribution, but as I mentioned before, the plasma, once you produce it, starts to expand. The pressure around it in the beam pipe is 0, and the pressure in the middle is a certain fixed value. So what happens is that the expansion is faster in the direction where the medium is short, because there the pressure gradients are large, and it is slower in the directions where the medium is long. And that then gives a change of the mean momentum as a function of the angle, and that is what we can measure in the detector. So what we can do, we can just look at the number of particles as a function of the angle, and this is shown here for a single event, just the angular distribution of particles, and you see that it is not flat, it's not isotropic. There are bumps and troughs, and these come from this azimuthally anisotropic expansion. Now you can see this in a single event because we have many, many particles in one event, but to appreciate it better, we take the sum of many events, and then you get, of course, better statistical precision. So that should now appear below. This works better, yeah. And you see here the sum of many events, and now you very clearly see 3 peaks, one here and 2 lower ones here. So we have the second harmonic and the third harmonic, and if you decompose this with the Fourier transform, you'll find that even the fourth and the fifth harmonic are present. And then how we normally present these data is not by presenting this plot, but is we present the amplitudes of these harmonics as a function of transverse momentum. And that is shown in this slide. So this is an overview of many, many different analyses, the work of many students, where we measure, for example, the second harmonic, so the elliptic deformation as a function of transverse momentum. And this is done for different particles. And one very nice pattern that you see here is that at low momentum, the low mass particles, they rise the quickest, and the intermediate mass particles, the kaons, they rise later, and then the heavier ones, they rise even later. And here in the middle panel, you see the same particles, and we add the deuterons, which are light nuclei, 1 proton and 1 neutron, and they rise even later. They have an even higher mass. So in this pattern of mass-dependent turn-on of the V2, it's very sorry, is indicative of collective expansion. If you have a fluid that moves at a certain velocity and that falls apart into different particles with different masses, the higher mass particles will have a larger momentum because the momentum is the mass times the velocity. And so this pattern shows that there is a common underlying velocity from this expansion that I mentioned before. And then we also do this measurement, the higher harmonics, so V3 and V4, so the third and fourth harmonic, for different particle types, and you see the same type of mass dependence. But I won't discuss that in much more detail. Now I'll switch to what do we learn from this? As I mentioned, it shows a common velocity, but we can also use this to learn about the plasma itself, about the properties of the plasma. And this is done by theoretical colleagues. So what they do is to make a model of the expansion with number of input parameters. And then they generate curves for our data. So here are the different measurements. So the V2 is shown here. And in this case, they also look at the yield, the numbers of particles, and the mean transverse momentum for different particle types. And they run the model for different parameter sets. And then they check which outcomes are consistent with our data, and that you see here at the bottom. And that way you can constrain the parameters. That way you can constrain the physical parameters using the data. And this is done, this technique is called Bayesian inference, this type of fit that they do. And here you then see for all the parameters, so there are many parameters in this particular model, the outcome of the fit. And some of these parameters are physically important parameters, and I'll show them on the next slide. Some other parameters are more, as you would say, technical parameters in the model, and it is good to see that you can constrain both the uninteresting and the interesting parameters at the same time. And one of the parameters is the viscosity, the shear viscosity, so the internal friction of the plasma. And you see here, this orange curve is the outcome of the fit that I just showed. It shows the shear viscosity to entropy ratio as a function of temperature, and it shows a slow increase. And and the value is about 0.1, which is a very low value. It's much lower than what you see in water and in helium, so in more common materials. And the fact that it is so small has to do with the fact that quarks and gluons are much smaller than atoms. But it also means, and this is a bit counterintuitive, that the interactions are very strong. The viscosity is proportional to the mean free path. So low viscosity means low mean free path, means many collisions in the fluid. And so what we have learned here is that the viscosity of the plasma is very small, and it's actually, there's a quantum mechanical limit which is about 0.1, so it is very close to the limit which is basically related to the Heisenberg principle, to the uncertainty relation. So the QGP we now know is very hot, it's very dense, and it has a very low viscosity. And now I want to show you what. So up to now I've talked mostly about things that are produced by the plasma, that come out of the hot soup, so to speak. And these are basically particles that are at low transverse momentum, below a few GeV. And there's another technique that you can use, which is using particles that probe the plasma, that are produced early on and then go through the plasma. The LHC is, in fact, that I showed earlier, is an example of that. The idea there is that you have what we call a hard scattering, in which you produce two particles that go at high momentum out of the plasma, and while they leave the plasma, they interact, and they, for example, radiate gluons. And with that, we can test the density of the plasma, and then we can also see how these particles slowly approach equilibrium. So they come in with a very high energy, they lose energy, and after a while, they become part of the plasma if they are fully, let's say, absorbed or stopped in the plasma. And of course, the plasma that we produce has a very short lifetime, so we don't see everything coming to equilibrium, but it is interesting to study how different particles reach equilibrium. The basic measurement there that we can do is shown here. So this is the transverse momentum distribution of charged particles, and it's now shown up to 100 GeV, so very high energies, much above the thermal scale, much above this 150 MeV that I talked about. And there are two sets of results. One is for proton-proton collisions, and one is for lead-lead collisions. And what you see is that the lead-lead collisions are shifted to the left. This is due to energy loss. Particles go through the plasma, they lose energy, so the distribution shifts to the left. And as I mentioned before, what we normally how we report the results is not like this, but it's in the form of a ratio of the nuclear modification factor, and it looks like this for these curves. So you see that there is a large suppression also for light particles. Now this suppression is not due to melting, but is due to energy losses, because particles end up at lower transverse momentum, and that then slowly increases as you go to very high momenta. And you also see here this bump at OPT, and that has to do actually with the mass effects that I discussed earlier in this elliptic flow. So the energy loss effect is dominant here, while here at low PT, this flow and expansion is the dominant effect. Now, what we can do this is done for all inclusive particles, which are mostly light flavor particles, so pions and kaons and protons. We can also measure this for heavy flavor particles. And the nice thing about heavy flavor particles is that the number of charm quarks that is produced in a collision, you can calculate from theory. And then every charm quark ends up in a particle that has a clear decay signature. So you can measure, you know the initial number, and you can measure the final number, so you can account for all of the charm quarks, basically. And here you then see the results for all the different particles. So the charged particles are in black, and there's different, so the pions are a little bit below, and then the heavy flavors are above. And one thing that's interesting to note is the blue here are non-prompt LHCs, so those come from beauty, from even heavier quarks, and you see that there the suppression is a little bit less, so those thermalize more slowly than the charm quarks. And then we can also measure this azimuthal asymmetry for the charm quark, which is shown here, and the values are actually quite similar to what we see for light quarks. And this is very interesting because the initial production of these charm quarks is isotropic. There's the same amount in every direction. So the fact that this is, and if you have an isotropic system, this V2, this amplitude would be 0. So this full signal is coming from interactions with the plasma, from particles that slow down and get redistributed by the plasma. And the fact that it is almost as large as for light quarks means that for charm quarks, we reach close to thermal equilibrium. And then you see a comparison to many model curves, which I don't go into detail in this case. And then the latest on this is, as I mentioned already a little bit, is the measurement, the comparison of charm and beauty quarks. So now on this slide, you see the V2, both are V2. On the left are these CC bar and BB bar pairs. So the CC bar are the blue points, and they show a clear V2, a large azimuthal asymmetry, while the BB bar shows no signal. The uncertainties are still large because we get fewer of those particles, so it takes more time to measure that precisely. But you see that it almost looks as if there's no flow, no V2 for the beauty quarks. And here on the right, you see the same kind of effect, but for what we call open heavy flavor. So these are mesons that contain a charm quark and a light quark, or a beauty quark and a light quark. But the pattern is the same, that the beauty ones have a much smaller signal than the charm ones. So this tells us that larger mass particles equilibrate more slowly. And this is one of the things that we want to investigate in more detail with some of the upgrades that we're planning. So this was a brief overview of some of the main results, trying to put them into context for how we use the measurements to understand the plasma properties. And now I would like to go back a little bit to the future program. So I showed you already the detector as we have it now, and we are now in what we call LHC run 3, I'm sorry, in 2024. And this data taking period will go on until the middle of 2026. And then there will be a break when there are no beams in the LHC, and where we can do upgrades, where we can improve our instruments. And this is a long one where Atlas and CMS, the other LHC experiments, will make a lot of upgrades. We actually did our major upgrades in this LS2, the long shutdown 2. But in the upcoming long shutdown, we have 2 upgrade projects. One is a forward calorimeter, a new detector to measure photons in the forward direction. And one is a replacement of the innermost layers of the inner tracking system. And I'll discuss in a little bit more detail what those are for and what that looks like. Then there will be a data taking period of about 4 years, and then the next long shutdown, and that is when we plan to install a completely upgraded detector. So this is a complete replacement of our current system with a more performance system. And we are now starting to plan. So we're doing R&D, and we are starting to plan for building this detector. And here in Mexico, many people are involved in the construction of what is called the muon ID, which is these outer layers of detectors with a big absorber to absorb all the other particles. And I'll also briefly give you a flavor of what's going on there. So now first the upgrades for the long shutdown 3, the ones that come up in a few years from now. This is this forward calorimeter shown in ALICE. So the interaction point, the collisions happen here. And the forward calorimeter is about 1 meter by 1 meter, and it sits around the beam pipe. So it measures particles that come at very small angles with the beam, which we call high rapidity. And this measure, the goal here is to measure photons, to measure the structure of the nucleus as it comes in, because we know that the nuclear structure is not exactly the same as the proton structure. And here you see the expected precision of the measurement that we can do with this focal, and this is the impact that it has on this nuclear structure measurement. To give you an idea of what that means, building a new detector. So this is a prototype of that detector. You see it consists of 3 subsystems. This is what we call a hadronic calorimeter, which we use to identify decay products from hadrons. And this consists of copper tubes with scintillating fibers inside. And they are read out with several photomultipliers, which look like this. So this is now being prototyped and tested. This was a setup that was used with a beam to test the performance of the detector. And then in front of this hadronic calorimeter, there will be the electromagnetic calorimeter, which consists of tungsten layers and silicon layers. And the tungsten are to convert photons into electrons and positrons, and the silicon layers are to measure these particles. And most of these silicon layers look like this. So these are so-called pad sensors, where each cell is about 1 by 1 centimeter, and we produce these arrays of 72 cells. And they will be then mounted with electronics to read them out. And then 2 layers out of the total will be instrumented with pixel sensors. So these are the same pixel sensors that we used for the inner tracker that I showed before. And there are individual chips here, which are about 1.5 by 2.5 centimeter, and there are, I think, 9 in a row on this particular model. And each of these has 500 by 1000 pixels. So each pixel is 30 by 30 microns, very high granularity. And we use that to distinguish photons that come to the detector with a small distance between them, because here at the forward direction, all the angles are smaller. So this is the focal prototype, and we have tested this in beams, and we are now moving towards production of this detector. The other upgrade is this, what we call the ITS3. So this is the replacement of the inner layers of the silicon tracker. And here you see a sketch of what it looks like. So the 3 green things are the silicon layers. I'll have a photo of what it looks like later on. The goal of this is to improve the pointing resolution, the precision with which we can extrapolate particles to the primary vertex. And we do that. That is the reason to do that is it improves the performance for the measurement of charm particles. The decay distance for those particles is something like 50 microns. So you need to measure very precisely where your particles come from to know that they come not from the primary vertex. And that also helps with the thermal electron measurement that I mentioned right at the start. Now here you see a test of this for this detector. So this detector is made out of silicon. And as you maybe know, silicon, if you have a silicon wafer, it is kind of brittle. It is kind of like glass. It breaks very easily. But it turns out that if you thin the silicon to 20 or 50 micron, it becomes quite flexible, and you can so this is one big silicon piece that is bent around in this case a metal stick to curve it, and it will in the end these kind of structures will go around the beam pipe, so very close to the interaction point, very thin, so it doesn't disturb the particles that go through, but you can still measure them. And then here you see it's connected to printed circuit boards to take out the signals. To show a bit more detail, so this is the most recent results on that. So we're now working on the design of the full sensor. This is a very large, one large sensor of 10 by 25 centimeter. Now this design is still ongoing, but we have test structure. So here's a 12-inch silicon wafer. And what you see here in the picture is that strip of 25 centimeter by 1 centimeter, which is a test. Tests so far look very good, so we are going on full steam, but there's a lot of work going on to learn how to do all of these things. And that you also see here, so this is another prototype, a mechanical prototype, where we learn how to handle this flexible silicon and how to connect it to printed circuit boards. Then I would like to switch to the LS3, to the upgrades for the more distant future. So this is an upgrade that we will want to do in about 10 years from now. But we need to have it ready in 10 years from now. We need to work on it now. And here on the left, you see a bit how LS then progresses in performance. So on the vertical scale, you have the pointing resolution. I mentioned we are now here, LS2. This ITS3 upgrade will improve the pointing resolution. So that is this arrow. And then with LS3, we want to improve it again by a factor of 3 to 5. And at the same time, we increase the readout rate, so the number of collisions that we can collect, and also the acceptance. As you see here, this new design, it can detect particles that go very far forward. So while a current detector measures only particles that go under more or less 45 degrees with the perpendicular. So the main upgrades are this, that you have forward coverage and that you can go very close to improve this pointing resolution. We need to go very close to the interaction point. And to do that, you need a retractable vertex tracker. So when the beams are at high energy and the collisions are happening, it will look like this. It will be, the first layer will be at 5 millimeters from the collision point. But when they put the beam into the collider, the beam is not so focused. And so you need to be farther away from the beam. And so we then can retract, we can open the system so that there's more space for the beams when they put the beam in the collider. So that the sequence will be, they put the beam in with the detector like this, they accelerate the beam, and then the beam will be more focused. And then we close the detector, and then the collisions happen, and we measure the collisions in this situation. Now, to give you a bit of a view of what the improvements are, what this can do for us in measurements, I wanted to come back again to this thermal radiation measurement. So here on the left, you see the temperature as a function of, energy, of collision energy. And you see in the blue line that if you measure this with hadrons, which are the particles that are the most produced, you go up first, but then it becomes constant. And this becomes constant because you saturate at the phase transition temperature. So all you can measure with the hadrons is the phase transition temperature. You cannot measure the temperature of the plasma itself. And to do that, you need to go to electromagnetic radiation, as I explained before. And so you see here the existing measurements, and you see from the large uncertainties that these are not easy measurements. And this is the precision that we expect to get with our LS3 upgrade. And you see here what this mass distribution looks like, and the temperature comes from the slope in this range. With this precision, we can not only measure the temperature, but the azimuthal asymmetry of this thermal radiation. So you can then see the effect of this anisotropic expansion starting from the early times, from before the hadrons were formed. And this is, again, this is a projection, this is the expected uncertainty, but you can see that this can be measured with very good precision with LS3. So we discussed already the melting of these quarkonia states, of the CC bar bound states. And I mentioned that the melting temperature depends on the binding energy. And so we have, so far we have measured mostly one state, the J-psi, and the psi2s is already difficult. And what we would like to do with LS3 is to extend this to what we call P-wave states. And you see here a theoretical calculation of 3 states and how these states, when the temperature increase, how they melt. And you see that the different states melt at different temperatures. The highest state melts first, and then the next state, and then the lowest state even may not melt so easily. And so that is what we want to study. Now, I'm not going into much detail there, but I wanted to show that with this muon identifier that I mentioned before, we measure this chi-c, which is one of these states, in E and in lead-lead collisions with a good precision. The significance means the relative uncertainty. And we can also measure more exotic particles. This chi-c1 is a particle that is a candidate for being a 4-quark state. So this is most of the particles we know are 3-quark baryons or 2-quark mesons. And this is an exotic particle that may consist of 4 quarks. And we can also measure that well with the LS3. On the physics program of LS3 is this one. So here you see, this is about this regeneration mechanism that I mentioned before. So at the LHC, we have many charm quarks, and they can recombine and form particles. And so far, we have measured this with J-psi, which are a charm and an anti-charm. But charm and anti-charm are also produced together. So it is not so easy to conclude about how many are formed kind of spontaneously and how many are formed in the initial collision. And so what we would like to do is measure the CC and the triple charm states, because those have to be formed by recombination. And you see here how at the LHC there's an enhancement as you go from single charm to double charm to triple charm. So far, we have measurements of single charm, but not of higher states. Idea of what it looks like. So one way we can measure double charm particles is to measure this, what we call Xi-CC, which will decay into a single charm with a pion and into a Xi meson, which is a strange meson, and two pions in the end. And this is a sketch of what such a decay looks like. And what you see here actually is the decay of the Xi baryon. And with our high precision layers, we can track this Xi baryon and we can see whether it points back to the primary vertex or not. And then we can recombine it with the pions to form this double charm state. The precision with which we can do these measurements is shown here. So this shows you the projected uncertainty for measurements of this double charm Xi state, and there is a similar state which is called omega, which we can also measure with LS3. Measuring the triple charm state is more challenging. There are very few of those, even though the enhancement from PP to LED is very large. We are not sure we can measure that with LS3. In the last few minutes, I would give you a glimpse of what we are doing to develop this new instrument. So this is another sketch of the new LS3, a bit more as seen in an engineering view, so to speak, where you see already the cables for all the detectors coming out. To give you a sense of what we're doing at the moment. So this is R&D that is going on for this retractable vertex tracker. So this is a prototype of the mechanical structure of these lobes that can be retract, that can be moved out of the way of the beam. And this is a first idea of how that could work. Now all of this, or how that could be kind of driven, all of this has to sit inside the beam pipe. So it is inside a vacuum. So it is very challenging to bring the mechanical manipulation from outside to inside the vacuum. And another thing that we're studying is the outgassing of materials. So if you have materials in vacuum, they sometimes, particular plastics, they outgas, and that destroys your vacuum. So we are testing which materials we can use in this design. A detector that we're working on is called the time of flight detector. So the principle there is that you measure the flight time from the production to the detection, and that gives you the velocity of the particle. And because we also measure the momentum, we can then determine the mass and we can identify particles. Now to do that, you need the time resolution of 20 picoseconds in this case, because we're quite close to the primary vertex. And we're working on a system of pixel sensors that have a gain, so that amplify the signal to get a fast response, so that we can get this time resolution. And we're currently, our current prototypes reach 75 picoseconds with sensors that are 50 micron thick. And what we are working on now is to make them thinner. This is a relatively standard process, but it is some chance that you break things, so we go slowly. And also to increase the gain, you see here how the gain can be changed, changes with the voltage. And with those two steps, we expect to be able to reach 20 picosecond resolution. A particle identification type of detector is shown here. This is called a ring imaging Cherenkov detector. This uses Cherenkov radiation to identify particles at higher momentum than the time of flight. And the way that works here is we have a layer of aerogel, which is a material with a refractive index that is close to 1, but just above 1. And when particles go through with almost the speed of light, they emit Cherenkov radiation. And we then measure the rings that makes photosensitive detection layer. And you see here the ring angle as a function of momentum for different particle types. So, if you know the momentum and you measure the opening angle, you can identify, the difference between protons and kaons and pions. And here you see a test setup that we have for this detector with an aerogel and a readout plane with a few silicon PMs at the moment. This is still a prototype. And here you see then the signals from this test beam, and you see here the angle. As for a test beam means you have a beam with one single energy. So you see here the pions and the proton peak separately because it's at fixed energy. And this shows that we have very good resolution, 5 milliradians, which is close to, or is actually better than we need for the final detector. last but not least, I wanted to show what we're doing for the muon identifier. So this is a project that some of the people in the room are involved in. Also there we have built prototypes and we do test beams. And currently we are studying 3 different technologies, multi-wire proportional chambers, RPCs, and scintillators. And scintillators are the baseline option and what most people are working on at the moment. So this is what it looks like. This is a scintillator bar with a wavelength shifting fiber. When the particle goes through, it creates a little flash of light that comes out via this fiber and is then measured with a silicon photomultiplier. And here on the right, you see the results from such a test. So this is the signal distribution when particles go through the scintillators at different momenta. And here you see the efficiency, and you see that it works very well. The efficiency is basically 100% at every place along this bar. So this was measured at different points along the bar, and they're 100 centimeters long, 1 meter. And it's very uniform and very high efficiency. So that looks also very promising. And with that, I would like to wrap up. So ALICE is a general purpose experiment for, I would say, for multi-particle QCD. Today, I focused on the quark-gluon plasma aspects, where we study the properties of the plasma, things like the temperature, the density, and the viscosity, as I discussed. And we are preparing upgrades for more precise measurements to understand better to get better measurements of the thermal radiation and of the approach to thermal equilibrium of charm and beauty quarks. And so all in all, there's a large ongoing physics program, many people involved in data analysis of data that we are taking these days, but also a good future with gradually improved detector performance, where we can make more and more precise measurements. And I'll just leave you with this picture from our control room when we started taking lead-lead collisions this year. So the heavy ion run from 2024 started on the 6th of November, and it actually finished this Monday or this weekend. And we collected a very large data sample to analyze again this year. So that was a very successful run. Thank you for your attention. Don't be shy. Do you have another microphone?
Thank you for your presentation, very interesting. And I have a question after the operating the detector. How would you be with a cooling system for taking the right temperature in the detector?
Thank you. So this is for the LS3 detector you were asking. And so there are 2 elements, because you asked about the cooling system, and for most of the detector, we keep it more or less at room temperature. So then you still need cooling, because all these electronic components, they produce heat. And for the tracker, so we are currently, so in the ITS, we use water cooling. So little tubes of water that go along the detector and cool down the electronics. For the LS3 upgrade, we are looking whether we can use air instead. So we can blow air at different places in the detector to cool it down, and that is to reduce the amount of material, the amount of stuff that we currently think we have to cool them down to about minus 30 degrees to keep the noise down. And this is more challenging. So we're looking at something which is called CO2 cooling, where you use liquid CO2, which has about the right temperature. And then you have thin metal pipes through which this liquid CO2 goes. But this has to be then at high pressure. And of course, you have to insulate everything to keep the temperature low. So this is something that needs study and R&D. Atlas and CMS, or at least one of them at the moment, have their tracker layers, or they're building tracker layers that will be cooled to -30 degrees. So it should be possible, but it is a challenging project.
Thank you for your presentation. It was very interesting. But my question is, what are some of the interesting open questions that heavy agencies have unsolved yet? Like, thank you.
Yeah. So there are several questions that we're working on. I think the two main ones that I also try to emphasize in my presentation. One is this temperature of the early phase. So at the moment, I mean, from everything we measure, we see that the temperature is above the phase transition temperature, but we don't have a direct measurement of this temperature. As I mentioned, the indications are that it is about 350 MeV, which is plenty high, but the precision is kind of low because you have this blue shift effect. You see that also at the relativistic heavy ion collider, the results are above the phase transition temperature, but the uncertainties are also sizable. So this is, I think, an important thing to measure, and the more precise we can measure this, the better we understand this expansion dynamics, because you need to know the initial temperature to know how fast everything expands. So this is a very important measurement, and it should be possible to do. Even with round 3 data, we get a first result, and then with LS3 the ultimate result. Now there's a related thing which I did not mention at all, but is related to chiral symmetry restoration, which is part of the phase transition dynamics. It's a bit hard to explain, so but it gives mass to some of the particles, to, for example, the rho meson. And with the high precision, these high precision measurements, you can also look at peak, and you can understand whether we see the chiral symmetry restoration, which is the part of the QCD phase transition. But the other thing I wanted to mention is this equilibration. So at the moment, we have evidence some quarks flow more than beauty quarks, so that heavy quarks, the heavier the quarks, the slower the equilibration. But there are several things that are still open there, and one of particular is open heavy flavor. These are particles that have a charm in a light quark or beauty in a light quark, and the flow can come from the charm quark or the beauty quark, but also from the light quark. And so one of the programs that we are pursuing is to understand that, to see what we do with what comes from the light flavor, what comes from the heavy flame.
Thank you so much.
So these are some of the examples. Yeah. Could you pass this behind you? Or, yeah.
Well, my question is, as you improve your efficiency of the detectors and technologies, are you expecting to find some new physics related to the quark-gluon plasma?
Yeah, so in our work, we do not expect what you call beyond the standard model physics, so particles that are not yet in the standard model. But we do expect new phenomena. So one is this chiral symmetry restoration, which is already happening, but we do not have experimental access to it. And this is one of the things that we will have in the future. Another thing that we have seen at the LHC, and that was for this mentioned this KFC state. So at LHC, we discovered a number of unexpected states. So as I mentioned briefly, most hadrons have either a quark and an antiquark or 3 quarks. And now we have a whole bunch of particles that have 4 or 5 quarks. And this is one of the recent ones. This was discovered by LHCb, one of the other LHC experiments, so-called TCC. So it has 2 charm quarks. And from the way it decays, we know that it also has 2 light quarks. And this is not excluded by theory, but we had never seen such states before. And so there's a whole program of studying these states and understanding how they form and how they are made up. And in this particular case, one of the questions is whether this is a tightly bound state, so where you have 4 or 2 quarks and 2 antiquarks in this case that are one bound state, or whether you have a what you call DD bar molecule. So you have a light quark, heavy quark combination that's bound and another one, and they are bound together like a molecule. And we don't know at the moment. And by studying the production rates and the V2, for example, but also by measuring momentum correlations between D and D bar, D and D bar states, no, D and D states, but different D0, D star, and D0, D star 0, we can actually measure so here at low momentum difference, you're sensitive to the interaction between these mesons. And so you can see whether it is possible that you can form a bound state, a molecule-like state from these mesons. So this was a surprise at LHC, the 4 and 5 quark states. We now have many potential states. For some, it is almost certain that they are 4 quark states. For others, we are discussing whether they could still be 2 quark states. And this is something that we will also continue with the more precise detectors. And then, of course, there can be things that we don't expect, and that would be the best. That would be the most interesting, but I cannot tell you what they are because we don't expect
them.
I have a question with the low PT regime that the experiment can measure for instance, the pions are measured until 0.15 GeV. In the Alice outbreak, there is a larger interval that the measure could be done for instance, 0.1 GeV or something. Are you trying to increase this interval?
Yeah, so this is quite a complicated question. So you're mentioning that at the moment we can measure particles from 150 MeV and up. And in LS3, we think we can also measure lower momentum particles, but there is a complex trade-off. So one of the reasons that you cannot go very low is that the particles have to go through all the detectors. So there's some detector material, and at very low momentum, they may be stopped by the detector. That sets one cutoff, let's say, and this cutoff is quite high for example, protons. The other cutoff is given by the magnetic field and where the detectors are placed, and this will be slightly better in LS3. Now, and another thing that you can do is you can go to forward rapidity. Oh, okay, so if you go to small angles with the beam, then because the performance of the detector is mostly driven by the total momentum, and if you go at an angle, you can have particles that have, for example, 500 MeV, but only 100 MeV transverse momentum, and that way you can also measure lower PT particles, but only at forward rapidity.
About the MunID configuration, and I know it will have a seal absorber, and in the letter of intent for LS3 mentioned that this absorber has the thickness of 0.7 meters. Why this thickness? Why not much larger or less?
Yeah, that's a good question. the absorber, I mean, the main requirement that we have is we would like to measure this Jape size down to 0 pt. And the Jape size has a mass of 3 GeV. So the two muons that come out have more or less 1.5 GeV if you are at 0 pt for the Jape size. So what we want is to have a muon system that can measure muons down to 1.5 or so GeV. And if you make the absorber very thick, then the muons, at lower momentum, get stuck in the absorber and you cannot measure them. This morning we saw actually a plot where you saw that the efficiency turns on at about 1 GeV. So I think there is still some room. One can try to optimize it a little bit, maybe make it a bit thicker or thinner, but to get muons at 1.5 GeV, we need to keep it around 70 centimeters. Yeah, you're welcome.
I want to make some comments first in Spanish, then in English. Realmente es un honor para nosotros tener al profesor Marco Van Dieven, que es el representante científico del experimento ALICE. Es una persona muy destacada en el área y tenemos el honor de tenerlo acá. Llegó el día domingo y estuvo en la UNAM el día lunes, el día de ayer estuvimos en el político. Todo eso tiene que ver con dinero. Hay que hablar, ¿no? Aunque no tiene demasiado allá, pero las universidades que participan en los experimentos del CERN están apoyando. Y como parte del grupo, el profesor Manuel Rodríguez, profesor Guillermo Tejeda, profesor Mauricio Martínez, y todos los demás estudiantes del grupo, mucho profesor solicitar. Then I will finish in English. Thank you very much, Marco. It was a real pleasure for us to have you here. As you can see, there is a lot of students trying to go to and do their bachelor thesis, master thesis, PhD thesis with us, with you. So, thank you very much, and thanks again.
Thank you.
Now they are doctoral students doing their doctoral thesis with us. Similar calculations they want to know what to do to work first. We're able to download some work from we are like how complete those. What's one possibility? Good question. I'm trying to think because we have the same summit students program. I think they are over beauty project. So, and if you work on a topic that also one of the students is doing work on the side, writing them, saying what they're doing, and ask whether they would like to visit for the whole country. Okay. So this program is mostly for member states. Mexico is not a member state, but there are other states that are not members. But still, I mean, let's say the best was to someone on still knows what they're working with, and they do have an idea of what to do better than they should do. Because they already know how to do it, really fast, and they can help you develop that is the best way to go. I mean, the other way is to it's a fellowship journal when you have to have a surgery with PhD, and then you can become a postdoc, and there also postdoc. Yeah, there's more than one, but the whole world one. Or you have to supervise and you to send you to serve for 2 weeks to live with somebody. What was? Yeah, there are several experiments that look at matter and some of the, but most of the instrumental facilities are in underground facilities, and you know what it is, or you know? And in theory, I don't know, I mean, and you do some meta in the community. Young students is the type of security problem. I don't know exactly how to do this work for everything. Who is it to go to the website to put a theory group and look who are there and you can the name. And you can look for the name and look for the paper and see whether one of them works and support you. Very good. Thank you very much. Nice to meet you. Nice to meet you. Recording.